Around 450 BCE, the Greek philosopher Zeno of Elea posed a series of paradoxes designed to challenge our intuitive understanding of motion, space, and infinity. The most famous of these is the Dichotomy Paradox. Suppose you want to walk from one side of a room to the other. Before you can reach the far wall, you must first reach the halfway point. Before reaching the halfway point, you must reach the quarter-way point. Before that, the eighth-way point. In fact, to travel any distance, you must complete an infinite number of smaller steps. Zeno argued that completing an infinite number of tasks in a finite time is impossible, and therefore motion itself must be an illusion. The mathematical heart of Zeno's paradox is the infinite geometric series. When we add 1/2 plus 1/4 plus 1/8, and so on without end, the total sum converges to exactly 1. Each term is precisely half the size of the previous one, so the ratio r equals 1/2. A geometric series with first term a and ratio r, where the absolute value of r is less than 1, always converges to the finite value a divided by 1 minus r. For our series, that is 1/2 divided by 1 minus 1/2, which equals exactly 1. The visual bar fills completely, confirming the paradox is resolved by the mathematics of limits. A second of Zeno's paradoxes involves the legendary Greek hero Achilles racing a tortoise. The tortoise is given a head start of, say, 100 meters. Each time the swift Achilles reaches the point where the tortoise previously stood, the tortoise has moved forward a little further. By the time Achilles covers 100 meters, the tortoise is at 110. By the time Achilles covers another 10 meters, the tortoise is at 111. This infinite series of smaller and smaller catch-up steps seems to mean Achilles can never overtake. Yet in reality, the infinite series of times converges to a finite moment when Achilles passes the tortoise. The resolution of Zeno's paradoxes came with the development of calculus and the formal theory of limits. Mathematicians define a series as convergent when the sequence of partial sums approaches a finite limit. The key insight is, the sum of infinitely many terms can be finite, as long as the terms shrink fast enough. Formally, the limit as n approaches infinity of the partial sum s sub n equals 1 for our geometric series. This means a moving object does pass through infinitely many subintervals, but each one takes proportionally less time, and the total time is finite. Zeno's error was in assuming that an infinite collection of non-zero quantities must have an infinite sum, a beautiful misconception corrected by modern real analysis. In modern physics, Zeno's name has been attached to a striking quantum phenomenon. The quantum Zeno effect, first described theoretically by George Sudarshan and Badhyanatha Mishra in 1977, states that an unstable quantum system can be prevented from decaying if it is measured frequently enough. Each measurement collapses the quantum state back to its initial undecayed state, effectively resetting the clock. The more rapidly and repeatedly you observe the system, the slower or effectively frozen its decay becomes. This is a direct quantum mechanical analog of Zeno's argument that constant observation interrupts progression. The effect has been confirmed in laboratory experiments using laser pulses on trapped ions, demonstrating that Zeno's ancient philosophical puzzle has real physical consequences at the quantum scale. Let us test your understanding with a review question. What is the exact sum of the infinite geometric series 1/2 plus 1/4 plus 1/8 plus 1/16, continuing without end? Option A, 0.99. Option B, exactly 1. Option C, 2. Option D, the sum is infinite and diverges. Think carefully about what the geometric series formula tells us, and about what Zeno's paradox reveals. Write your answer and a brief explanation in the comments section below. We read every reply.